Hey guys, Mr. Mises here, and in this video I'd like to talk to you about using all the stuff that we've learned so far. First derivative test, second derivative test, concavity, increase and decrease, all that stuff in order to do a really good sketch or curve sketch of a function using our extrema and our points of inflection. So let's go ahead and get started on that. Shrink them down. All right, so we're going to use a similar recipe that we did early in Unit 1. We did part of these. We did this, and this. And this here we did not do is the last three. So we're going to add in the calculus here in order for us to, let me move this desk over a little bit, in order for us to do these problems here. So let's take a look at an example, shall we? We shall, because I'm the one doing the video. So we're going to start here with finding the domain. So first I have f of x, f prime, and f double prime. So we don't have to do, in the examples that I have, I'm not actually going to do the derivatives, but I'm sure that in the problems that you do, you are going to have to find the derivative, find the second derivative, set equal to 0, blah, 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 blah. But for these, I'm already giving you the derivatives, so you don't have to do that calculus part. So let's take a look at the original function, the domain. Well, in our denominator, if we set that equal to 0, we can't really solve for x, so the domain here is going to be all real numbers. Okay. Our vertical asymptotes. Well, again, if we set x squared plus 1 equal to 0, we really can't solve that for x squared, at least not in the real plane, so there are none. There are no vertical asymptotes. Are there any holes? No, not in this case. Same thing. We don't have anything canceling out, right? We would need to see these cancel out. You'll see that in another example that I do. X-intercepts. To find the x-intercepts, we're going to go ahead and take 2x cubed and set that equal to 0. And we're going to get x equals 0. When we plug that back into our equation, our function, we're going to get 0. So our x-intercept is 0, 0. Our y-intercept is when is when is the x value going to be? Well, it's the same thing, right? If 0, 0 is the origin. Or with this one, we're just going to plug 0 in for x. And we're going to get 0, 0. What's the end behavior? Well, the end behavior, remember, is our limits. So the limit as x approaches infinity is going to be, it looks like it's going to go to positive infinity. And the limit as x goes to negative infinity is going to go to negative infinity. All right, so that's my end behavior right there. So it's going to go down like this, and let me use a different. It's going to go down like this, up like that. All right, at least that's what I know is going to happen for the end behavior. Is there any symmetry? Well, this is an odd function divided by an even function. And so an odd divided by even is going to give me an odd function. So this is going to have origin symmetry. All right, now we've done all the pre-calculus stuff, so let's take a look at the calculus stuff. Relative maximum. Well, am I going to have a relative max? How do I know that? I'm going to set my derivative equal to 0. So f prime, I really only need to set the top equal to 0. And I'm going to get 2x squared equals 0, x squared plus 3 equals 0, which is just going to give me x equals 0. So this is my possible critical number. Okay, it's my critical number. And if I check my f prime, let's check negative 1. If I put negative 1 here, that's all both going to be positive. If I put positive 1 in here, it's going to be positive. So this is not going to change, right? It's going to go increasing, increasing. So there's no relative maximums. In fact, there's no relative minimums either because I don't have anything changing. It's strictly monotonic. Don't worry, guys. In the next, I have 3 examples, each in a separate video. So you're going to want to check that next video and the next video after that. Those 2 videos, I do have critical numbers and things that I have to check for. Okay. So what about my points of inflection? Well, I'm going to take my second derivative now, which is negative 4x, x squared, minus 3. And I'm going to set that equal to 0. And I'm going to get negative 4x equals 0. And x squared minus 3 equals 0, which is going to give me plus or minus root 3 and 0. So now I have something to really check, right? So let's check this out. I've got f double prime, negative root 3, 0, and root 3. These are all my pips, my possible points of inflection. Oh, let me pause that. All right, so we're going to test these here. And when I put this in my, when I put it back in here and I put these, test these, I'm going to get plus here, minus here, plus here, minus here. Here, look at that. It's concave up, concave down, concave up, concave down. So I do have points of inflection. Actually, all of these are inflection x values. So I'm going to plug these values back in my original to get my points of inflection. Okay, again, you're going to plug this x value back into, let me shrink this down, back into your original function f, okay, to get your y value. And I'm going to get 0, 0, root 3, and 3 root 3 over 2 when all is said and done, and negative root 3 and negative 3 root 3 over 2 when I get all that finished. All right, so now I'm going to graph this guy. And I'm going to plot those points of points of inflection. It's going to do damage. Points of inflection right here. a point of inflection and a point of infection are two very different things, right? Okay, so I'm going to go concave down, concave up, concave down, and then concave up again. All right, it's like a little snake. And I'll probably do this a little bit curvy like that. There we go. All right, and there's my graph. All right, so there's one example of using our curve sketching and calculus to sketch a curve. Again, we're going to have 2 more examples. Watch those 2 videos. We'll catch you soon in the next one. Bye.